Gradings, electromagnetics 321 class. Um, so I'm out of town this week, and the instructor that I had arranged to take over the class can't do it. And so I'm going to make a couple of videos and show these videos, and I'll give an assignment that will be due next week when I return. So this is the first of two videos, I believe. Hopefully I can get the other one done. And what I'm going to do is I'm going to introduce chapter 2. So I know you turned in an assignment last week. Hopefully you did okay in that assignment. I'm giving another one today, and it will be due next week. All right, so chapter 2 in our textbook is now going to introduce Coulomb's law, which you should have learned about in your physics class. And I'm going to remind us that there is a foundational equation that we discussed in class maybe a week or two ago. And that is the equation for the electromagnetic force. And I likened it to mechanical force, F equals ma. But for electromagnetic fields, the forces that they create are proportional to the charge of a particle or a material or a mass, whatever, times the electric field plus that same charge times V cross B, where V defines how the particle or the material is moving, and B is a magnetic field. So first of all, you should understand that in order to experience an electromagnetic force, there has to be a charge. And in this equation, Q is the charge. I didn't write it on the slide, but Q is the charge. So that's kind of like a foundational equation. And you're going to find in engineering in general, we care a lot about forces and how they act on different entities. So yeah, F equals QE plus QV cross B, foundational principle. Okay, so Coulomb's law. Like many laws in the science or the physics world, right? This is not something that was made up in somebody's mind. It was based on an experiment by a French physicist named Charles Coulomb, or maybe Charles Coulomb. And he did a series of experiments and described the forces of attraction and repulsion on two charged spheres. So that's how Coulomb's law was established. It was based on experiment, something that was observed in the physical world. And he basically observed that if you have two charged particles, that they would have a force either of attraction or repulsion. You may understand that oppositely charged particles attract, and if two particles have the same plus or minus charge, they will repel each other. Anyway, the force is proportional to some constant K and inversely proportional to the distance between the two forces. So in the image that you have here, you have two charged particles, Q1 and Q2, and they are separated by some distance R. And they're going to experience repulsion because they are like charges. So Q1 would move if you were to restrain Q1 in some place and restrain Q2 at some place, then let go, you would see that both of the charges would move away from each other. So this is the equation that was observed by Coulomb, that you have the force would be proportional to the magnitude of the two charges. It will be inversely proportional to the distance between the two charges. And it would be proportional to some constant K, where K turns out to be 1 over 4 pi epsilon naught. All right, so we've been able to determine a actual value for K. And if I can make the slides work, let's see. How do I move? Okay, all right, there it is. So this epsilon naught is called the free space permittivity. And it has this value 8.854 times 10 to the minus 12 farads per meter, or 1 over 36 pi times 10 to the minus 9 farads per meter. This is the permittivity of free space. So if you have two charged particles in vacuum or just air, so to speak, then you would find that K would be 1 over 4 pi epsilon naught, where this is the value for epsilon naught. All right, so by substituting in the K into the equation for the force, Q1, Q2 over 4 pi epsilon naught, R squared. Again, R is the distance between the two charged particles. So let me pause. Okay, so again, the direction of the force is going to be dependent upon, what is the type of charges that you have. So what we usually do is we describe as the force at Q2 due to Q1, or the force at Q1 due to Q2. So in this particular case, we're looking at an equation. We want to determine what is the force at Q2 due to Q1. That's what we're going to do. And as you know, force is a vector. So forces have a direction. Even if you go back to that original slide here, you can see that this is Q2. It's going to experience a force, and the force is going to be in this direction to the right. Yeah, to the right, right? So, and this one is going to have a force that's going to be to the left. So in order to do this equation here, we have to do a vector equation, basically. So the vector information is not really obvious here, right? You need to take care of that. So this is the beginning of how we're going to figure out what is that direction for that force. The magnitude is obvious, Q1, Q2 over 4 pi epsilon naught, this 1 over the distance squared. But the direction, how do you find that? Well, the direction at Q2 due to the presence of Q1 is going to be a vector that's along the direction from 1 to 2, right? So that's going to be it's going to be in this direction, right? So how do you figure out what that vector looks like? Well, you don't want to change the value of the magnitude, so you want to use the unit vector. And so this unit vector A12 is in a direction from Q1 to Q2, because at Q2, the force is going to be in the same direction. It's going to be directly going away from Q1. So how do you find that unit vector, right? You may recall from your work from the first couple of weeks in class that a unit vector is going to be, you can define a unit vector by taking the R12, take this vector and divide it by its magnitude. So R12 over the magnitude of R12 is the unit vector. R12, or a vector from Q1 to Q2, is the same thing as R2, R2 being a vector from the origin to the point where Q2 is located, minus R1, again, a vector from the origin to the point where Q1 is located. So R2 minus R1 is R12. And then the magnitude of R12 is what goes into the denominator. So you probably remember how to do R2 minus R1 based on your first couple of assignments. At least I hope you do, right? So R2 and R1 have an X and a Y component, right? So R2 minus R1, you take the X components and you subtract them. That's your X direction. You take the Y component and subtract them. That's your Y direction. And then the magnitude is the square root of the X component squared plus the Y component squared, right? So right now I'm talking about two-dimensional space. In three-dimensional space, you just add the Z component in there. All right, so remember also that the equation is F is equal to Q times E, Q times E. All right, so if F is equal to Q times E, which is also equal to Q1, let me go back, is equal to Q1, Q2 over 4 pi epsilon naught R12 quantity squared times the unit with the unit vector in the 1, 2 direction. All right, so what part of this is the Q and part of this is the E. In other words, this F2 is equal to all of this, which is equal to Q times E. So if that's the case, then the force at 2 is we're gonna treat the charge at point 2 F2 at Q2, we're going to treat it as a test charge. In other words, it can take on any value, but just consider it to be a test charge. And so we're saying the force at the test charge is equal to Q1 times the test charge, the test charge itself, the magnitude of the charge of the test charge. The coulombs, how many coulombs is it? Times Q1 over 4 pi epsilon naught R12, R12, but R1t squared times the unit vector in that direction. All right. What we're saying is that this portion right here of our term is our electric field. This is the E, including the vector. And this is the Q. F is equal to Q times E. So here's an expression then for the electric field. And this is the electric field created by Q1. So our test charge, Q sub T or Q sub 2, placed inside of an electric field due to Q1 will experience a force in the same direction as the electric field, right? I'm gonna go back to the very beginning. We said that this was a vector equation, right? So if you don't have a magnetic field present, just forget about this part for right now. Then you can see that the forces that the charge experience are going to be in the same direction as the electric field. Because charge Q doesn't have a direction, it's only a scalar. E is the part that has direction. This is the vector. So if these two vectors are proportional by a scalar, then these two vectors are in the same direction. All right. Back to here. Okay. So this electric field is based on the presence of Q1. It creates a field around itself, an electric field. And if you place another charge inside of that electric field, it will experience a force. And the force will be either attracted towards Q1 or repulsed. I think repulsed is the right word. Repulsed from Q1. The units for an electric field is newtons per coulomb, right? Forces in newtons, F over Q, newtons per coulomb, or more often you'll find it written in volts per meter. So newtons per coulomb and volts per meter are equal to each other. You just have to get the the units correct. This is metric units as opposed to English units. But anyway, you can write electric field. It's a measure of how many newtons of force you'll get for each Coulomb of charge in your material or in your particle. So I'm gonna say right now, take a pause. We said F is equal to Q times E. Forgetting about the magnetic field component right now. F is equal to Q times E. Based on experiments by Charles Coulomb, we know that the force between two charged materials or charged spheres in his case could be expressed as Q1, Q2 over 4 pi epsilon naught r squared, where r is the distance between the two particles. And the direction of the force will either be directly toward each other or directly away from each other, based on whether or not the two charged particles or materials or spheres are similarly charged, plus, plus, or minus, minus, or have opposite charge, plus, minus, or and minus, plus. Okay. And we further said that because F is equal to QE, that the electric field E is due to the presence of one of the charges, either one. And the electric field that either charge produces is Q, where Q is the charged material, divided by 4 pi epsilon naught. And it's the electric field varies as 1 over the distance squared, how far you are away from the particle or the charged material. So if you're right next to the charged material, R is a very, very small number. You square it, put it in the denominator, then the magnitude of the field is large. But as you get further and further away, the magnitude of the field falls off as 1 over distance squared. All of that is true. Well, all of that can be deduced from this expression that Coulomb was able to write down. All right, so I think we already talked about this really in the sense that you have a charge material, point charge is what we're starting off with, located at some position in space. And that position in space is X prime, Y prime, Z prime. And so we call this vector from the origin to your charged particle. We call that vector R prime, and it points to the location of your charged material. Okay. If you wanted to find out the electric field at some point P, which is X, Y, Z, then the electric field is going to be Q over 4 pi epsilon naught times the magnitude of this distance squared. And the direction of the field is going to be in the direction pointing from the source, the point charge source, to the point P where you're trying to compute the value of the electric field, right? So you need to write down what is the unit vector in that direction. And we know that the unit vector is going to be R, which is this vector here from Q to P, divided by the magnitude of R. And we know that R is equal to this little r minus this little r prime. Okay, so those things are true. And if we were to write that out, because of the fact that the author has given us X prime, Y prime, Z prime for our source of our electric field, and X, Y, Z for the point at which we want to compute the value of the electric field, we know that's going to be Q over 4 pi epsilon naught, R minus R prime, divided by the magnitude of r minus r prime squared, and then divided by the magnitude of r minus r prime. So this part right here, that's where we get our unit vector. And this is where we get the magnitude of our electric field. Okay. All right, so let's just plug in our values. We know what we have r minus r prime in the numerator. These are vectors. And in the denominator, we have magnitude of r minus r prime quantity cubed, right? We have a square, and then we have an extra one here. So now we have it cubed altogether. Well, r minus r prime is x minus x prime, a sub x, plus y minus y prime, a sub y, plus z minus z prime, a sub z. All of that times q over 4 pi epsilon naught times x minus x prime quantity squared, plus y minus y prime quantity squared, plus z minus z prime quantity squared. All of that inside of brackets to the 3/2 power. Okay, so how do we get 3/2? Well, the magnitude is the square root of the sum of the squares of the components, but we're cubing it. So a square root cubed is 3/2. Okay. So that's how you did it. So if I gave you that x prime, y prime, z prime was 1, 2, and 3, and this is 3, 4, and 5, you just plug in everywhere you have x prime, put in 1, y prime, put in 2, z prime, put in 3, and for x, y, and z, 3, 4, and 5. Same in the denominator, and crunch the numbers. Okay. Now, I hope you understand when you're doing problems, don't put in actual values. Don't evaluate and crunch the numbers until you get to the very end of the problem. It's always better to solve things in terms of symbolic notation, and then at the very end, you can put in numbers. Okay, so the last thing I'm going to talk about in this video is the principle of superposition. Superposition, hopefully you recall this in circuits class. We talked about superposition. If you have more than one power supply in a circuit, you can solve the circuit from one power supply and then do it again and solve it for the other power supply and then add the two together. The same thing applies to electric fields. So let's just say you have two charges located in positions in space. Q1 and Q1 is at some position from the origin to some point P1, and then Q2 also at some position in space from the origin to some position here. All right, so now you got two particles that are charged, but they are restrained and held in a position in space. They're not going to move. The question is, what is the electric field at some third position in space? So we're going to say some point P. What is the electric field right here? Well, if you're standing right here, you would find that there's a field due to Q1 and there's a field due to Q2. And the total field will be the sum of those two fields, right? So basically, the electric field at any position in space is going to be a superposition, a sum from 1 to n, where n is the number of point charges or the number of material, what's the word I want to look for here? Number of sources of charged material that can create an electric field at the point where you're trying to compute the field. So you do the Q over 4 pi epsilon naught, 1 over the distance squared times the unit vector. You just do the same process for each one of the charges. If it's 5 charges, you do it 5 times and add them all together. And that would be your total electric field. They all have an X component. They all have a y component. They all have a z component. You add the x's together, the y's together, and the z's come together to come up with a final vector for the electric field. So here's an example. It says find E at P using that expression that we had, that the electric field is the superposition of all the charged particles. So how many charged particles do we have? We have 1, 2, 3, 4. I don't know if you guys are seeing this thing here. Let me do this. I think you have 4. So let's see. Here's P1. Here's P2. Here's P3. And here's P4. They're located at the corners of a square. 1, 1, 0, minus 1, 1, 0, 1, 1, 1, and 1 minus 1, 0. Okay. And here's your point, P111. That's where you want to compute your electric field. Right. So you would take each one of those, you would and compute a value for the electric field due to the point, to the charge at P1, another one for the charge at P2, another one for the charge at P3, and the last one is for the charge at P4. Okay. And add them all together. And that's the principle of superposition. So I'm gonna pause for a second here. Okay. So the second half of the slides, I'm gonna do another video. That's where we're talking about distributed charge as opposed to point charges. But in the meantime and in between time, the assignment that I'm giving you for that's going to be due for next week is an assignment where you will be asked to calculate what are these forces and what are these electric fields due to charged point charges. And so when I get back, we'll have another assignment where we'll deal with distributed charge, which is the second half of the chapter. Okay, so that's all for today. I'll look forward to seeing you all when I get back next week.